Hi, in this video, we want to take a look at linear regression in the context of supervised learning. All right, so linear regression is by far the most well-established supervised learning model, most well understood. Statisticians have been using this for a long time. They, like we have studied it to death. And there are a lot of tools within the lane of statistics for supervised learning and just for inference. Now, what we're going to do here, we're not going to really worry about the inferential and the statistics point of view. We're going to look more at like the data mining supervised learning aspect of it. So our main focus for this is I want to use this type of model to predict something that will happen in the future. Now, linear regression is by far the most foundational technique in supervised learning. It's straightforward, it's interpretable, and the algebra is pretty easy to understand. It's as simple as we could mathematically get. It's got a rich history and a huge amount of tools to help us, get better models. All right, now some things to think about is, first of all, what are we doing from a math point of view when we're doing linear regression? Well, what we're trying to do, we're trying to find the line or the higher dimensional multi or hyperplane that best fits our data. And so we're trying to do a simple, from a geometry point of view, a simple line, simple plane, simple three-dimensional space that helps us predict our target variable as well as possible. Now, there's some major advantages, but also some significant disadvantages to using linear regression. First and foremost, linear regression, because of the matrix aspect of it, it's fast. I mean, it's fast to train. And so if I need to produce a model quick without a whole lot of fussing over stuff, or without having to wait for it to compute, linear regression is a good choice as long as the data it isn't too big in terms of the matrices. Now, it's mathematically simple to interpret, especially when we have fewer predictor variables and we have simpler formulas involved. Now, something that's very nice is that we have special formulas for identifying like outliers and performing leave one out cross validation that only linear regression has, or offshoots of it, that we can use to do other things in machine learning that would take a lot longer to compute. And so this improves the accessibility of features of machine learning that we don't have otherwise. Now, the theoretical pencil and paper, like proofs aspect of linear regression, is by far superior to all other models that we could possibly use in this lane. Now, for the purpose of prediction, this doesn't really help us because the train validation test split aspect works out very well. But for the purpose of like deeper understanding, or maybe giving deeper explanations to like stakeholders who have a stronger statistics background, this is very nice. Now, the interpretability, we have like so many tools to help us out on this. It's relatively easy to work out things. We can figure out what's going to happen if the predictor variable goes up by 1. We can see how much on average we expect the target variable to change. Statistical inference, we have tons and tons of hypotheses tests at our disposal when we do linear regression. And also, something I like to do is I use linear regression as my benchmark model. And so what I'm doing is, as I'm working on a project, if I have a very complicated model that only does a little bit better than linear regression, then it's probably not even worth doing the extra complication and the risk of overfitting. Now, there are some major disadvantages to linear regression. First and foremost, it's sensitive to outliers. So we have to consider handling outliers and anomalies before we fit our model. For data preparation, compared to like tree models, random forest, stochastic gradient boosting, linear regression is very sensitive to how we prepare our data, specifically our numeric variables. We also run the risk of overfitting. And so so overfitting is always a risk. And here, when I'm talking about overfitting, I'm talking about specifically having more predictor variables than I should. So too many cooks in the kitchen, too many predictor variables in the model. Other models, such as random forest, will kind of like mute out some of the impact, or maybe lasso or ridge that we'll talk about later, uh, will kind of compensate for what's going on. Standard linear regression does not like catch that for us. And so we need to be more selective on our variable selection phase. And so, there's no variable selection automated for us. So we have to worry about that. And then we also need to know what model we want to use. And so if I'm going to be using a numeric variable, maybe in linear regression, I should use square root or possibly squaring it, or maybe a logarithm. We have to figure that out on our own. Like the tree models will set up splits that really it doesn't matter as long as it's a monotonic transformation. It doesn't matter if I was to do the raw data or the transform data. So if I had positive predictor variable and I did square root or the regular value, the tree model will give me the same performance either way. Not the case with linear regression. So we have to figure out our feature engineering more than with other types of models. Now we have some assumptions with linear regression. First and foremost is that the model that I'm using is the correct model. If this one is wrong, then I've got problems. There's nothing I could like the algorithm can't overcome me doing a garbage in, garbage out on the formula. We need to have independence between observations. We want to have the residuals of the error should be constant with respect to the predictor variables. Now, the normality we actually don't need for supervised learning. This is for hypothesis testing. And so here we want the residuals to be normally distributed with a constant variance with respect to the predictor variables and a mean of 0. And also we make the assumption of no multicollinearity. And so that idea is when, so imagine that I have 3 predictor variables that nearly perfectly can predict a 4th predictor variable. Then I have multicollinearity because this 4th one is redundant. And so no multicollinearity is saying we don't have any redundant predictor variables. Other model structures such as random forest, if I have this situation, what it will do is it will just kind of pick one and the other ones won't get as much love in the feature importance. And so we don't run as much of a risk of overfitting. Linear regression, we always have to worry about this pretty heavily. So now let's look at simple linear regression, the simplest version we could have. We have our predictor variable, and our equation that we're going to focus on is that I'm going to take my predictor variable times a coefficient plus an intercept, which is also called a bias in the neural net speak. And so then y is our dependent variable, our target variable. X is the one independent variable we have to work with. We have an intercept and we have a coefficient. And this coefficient gives us, this is on average, if I increase the predictor variable by 1, this is the average amount that we would see our target variable increase on average. Now that is, assuming I have the right model structure and I'm not missing anything from the model. Now, multiple linear regression is similar, but now you can see that I've got more predictor variables, more coefficients going on, and I still have this error term, which is assumed to be normally distributed, mean 0, and constant variance. Now, if I look at this, if I want to actually fit this equation, we're not going to do this manually. How we're going to approach this with matrix algebra. And here is the matrix formula for the formula I have here, where we can see that we're saying that the intercept corresponds to a predictor variable of all ones. And then here I have coefficients times the columns. And so that's exactly what we're putting here in matrix formation. And so now the formula for fitting beta, I should have put a beta hat on this, is that we will take the product of the predictor variables with their transpose, inverse of that matrix, multiplied by the transpose of x, multiplied by y, and this will give me a vector of the coefficients. So that's how we fit this. This is the least sum of squares residuals formula. All right, and so now this formula is very nice in that it's compact. It's good for doing theoretical work, especially when we treat x as constant values, y as having the random component. The theory aspect is very nice. If you look at my other YouTube playlists, I go in full depth of the theory of linear regression, and much of it is just based off of that equation. Now, for model fitting, what we're going to do, we're going to use this formula here to work this out. But there's something that we don't really talk about in statistics too often, is that this formula here isn't very good for the purpose of having a computer do it. It's theoretically right, it's mathematically correct, but from an actual execution, there can be problems. Inverse matrices can be problematic when it comes to numerical stability. And so there's actually better ways. There's faster ways and numerically more stable ways and numerically more consistent, more accurate ways than to use this formula. So what we're going to do when I tell R, SAS, Python, whatever to do this calculation, it's not going to use this formula here. It's going to use a numerical linear algebra formula that you can, like, I say that a lot during my doctorate work, but we're not going to talk about here. It's wonderful stuff. It's exciting stuff. It's interesting, but it's outside the scope of this video. This formula here is important for theoretical stuff. If I want to figure out like do a pencil and paper proof on, to get deeper understanding of the model, this is the presentation that is easiest to work with. All right, so let's go ahead and start building some models. And so, as always, I start out by setting up my workspace. I'm going to set it up so that I only have 5 digits being printed. I'm going to try and avoid scientific notation. And I'm suppressing warnings from the output from R, just because I tend to go, I tend to live in both the tidyverse and base R way when I do my coding. Sometimes I violate tidyverse rules, but are perfectly fine for executing. Remove any objects from my workspace to make sure I don't have any artifacts causing problems. And I'm going to be using piping, so I'm using the McGritter package. All right, so I'm going to load my data. Now the data I'm going to use is from Kaggle, the house price regression competition data set. And in this data set, I have a training set and a test set. The test set, I don't know any of the target variable values, so we're just going to completely dump that. We're not going to worry about that. You'll notice I'm using readr. Readr is one of the faster ways to read a CSV, and something that will speed up the process a lot, and this is true across the board, whether you're in Python, R, SAS, or whatever, is if you specify what are your data types for each column, this can greatly speed up reading in a file, especially if it's a large file. And something I like to do to make sure I have syntactically correct names is I use the janitor make clean names function. Now here, I'm not concerned with any of the data that I don't know what the value is for the target variable, so I filtered that out. And as it's set up at this point, when I have it loaded into my system, I have only a training data partition. I don't have a validation set. So I'm going to go ahead and do approximately 50-50 train validation split, and I'm randomly selecting. All right, so right out of the gate, I'm going to do a linear regression model, and I'm going to include all of the predictor variables possible. Now, I would not do this in real life. This is not a model that I would put into production, but this is a model I would start out with and start exploring with and start working through things. And so here in my formula, you'll notice I have the target variable on the left of the tilde, and I have all of my predictor variables with a plus sign in between them in the formula. The function in R for linear regression is LM, linear model. And then I specify my data, and you'll notice that I'm reducing it down to just that training data. I'm filtering out the validation data. Okay, so I mentioned previously that we can have problems with multicollinearity, and we have to do our variable selection before to be able to get a reliable, trustworthy model. And so before the video, I went through, I did forward selection, backwards elimination, and stepwise forward back selection. And I already did that. And so backward elimination, you'll notice that there's fewer predictor variables. Backwards elimination takes the full set of predictor variables and then one at a time removes each model and compares, did my model improve in terms of AIC? There are other measurements to use. I chose to use AIC because I'm using the mass package. And so take the full set of predictor variables, go down the list, remove one, refit the model, put it back. Remove one, fit the model, put it back. Remove one, fit the model, put it back. Do that for all the predictor variables. So if I had 100 predictor variables, on the first step, I would have 100 little submodels. And then I'm going to see which one is best. And so that determines which one gets kicked out of the predictor variables. Now, I'm going to repeat this process until we can't improve by an AIC criteria. Now, forward selection is the same thing, but in reverse. So previously in backwards elimination, we started with a full set, and then we kicked them out one at a time until we reached a stopping criteria. For forward selection, I'm going to start with an empty model. I'm going to add a variable, evaluate it, evaluate the model. Okay, remove it, add a variable, evaluate the model, remove it, add the variable, and do this over and over and over until I reach a stopping criteria. For how I set it up, it was for when the AIC no longer improves. And so what happens is I'm going to go through, and by doing forward selection, I get this set of predictor variables. All right. Now, forward selection, which is both in the mass package, what's going to happen here is that we're going to go through and we're going to do forward selection, but we're also going to take a step back to double check to make sure that everything should stay there. And so, this is forward selection, add a variable, check to make sure that we can't improve by kicking something out. Add a variable, check to make sure that we can't improve by kicking something out. Add a variable, check to make sure that we can't improve by kicking a variable out. Do this until we reach a stopping criterion. And that is forward back selection. All right, so if I have big data, I want to use forward selection. Forward selection is the fastest of these. If I have a big data problem, backwards elimination can take a really long time. And I've found that generally in a big data situation, the amount of time for computation isn't worth it. If I have a lot of predictor variables, backwards elimination can be a problem. Also, forward back is kind of like in between because it starts in the forward aspect, but still goes that backwards. If I'm in a big data situation and I'm pressed for time, I'm only going to do forward selection. But my feel is that backwards elimination does a better job of making sure you don't lose something that you wanted to keep. And it does a better job of having a more complete capture of what's going on with your predictor variable and your target variable. All right, so now that I've got my models, I've got 4 models. I have the full model, backwards elimination model, forward selection model, and forward back selection stepwise. I'm going to tack on the predicted values of each model, and I'm going to tack on the residuals of each model. All right, so now I want to talk about evaluating my model. So now there are tons and tons of different ways to do this. There are tons of tools where I can just drop a linear model in straight and it'll run it. I'm going to do a few different things. So here, first of all, I'm going to look at just the R squared. So I'm going to look at the correlation between the predicted value and the actual target value. And you'll notice that once again, I'm doing it for my train sets and my validation sets. And I've got my backwards elimination. I have each of my models here set up. And so I can compare. Of course, we want the best value on our validation sets. So it looks like backwards or both. I believe these are the same model. It's typical for the forward back selection process to actually be equal in terms of predictor variables, equal to backwards or equal to forwards. That happens surprisingly often. Remember that we always want to look at our train statistic and our validation statistic to check to see like how much is overfitting an issue. Here, I'm feeling okay with it. Now there might be a little, there might be a little bit of overfitting. If I have a lot of rows of data, typically we'll be okay with having collinearity if I have enough variables to compensate for it. Now we can also use the adjusted R-squared value. The adjusted R-squared for the train statistic is automatically in the linear model output when I hit the print button. And then the mean squared error is where I just take the residuals, the difference between predicted and observed, right here, square the values, then take the average. That's the mean squared error. Now, another one that's important for us to talk about is also the root mean squared error. So mean squared error, you'll notice that I'm taking the square of the error. Well, that means that if I'm measuring, let's say in feet, if my target variable is in feet, then my mean squared error is going to be in feet squared. What does that mean? How do I interpret that? That's kind of difficult. So typically, we talk more about the root mean squared error. We take the square root of this. Now, another one that's important is the mean absolute error is that here, instead of doing a square value, I just take the absolute value of the error and then take the average. I prefer mean absolute error because it's easier to articulate to my stakeholders that here's the average error. Now, mean squared error does a better job of avoiding large mistakes, large errors in the model. Whichever one is more important, go with what works for your project. Now, linear models have by far the most tools for analysis and understanding what's going on and doing diagnostics. And so we can look at histograms of our residuals, which we want to see as normally distributed. We can use QQ plots of the residuals, and we can look at scatter plot of target variable by predicted value, and we can also look at scatter plots of our target variable by individual predictors to help us understand what's going on. And so if I have a linear model in R, the plot function gives us up to 6 default plots right out of the bat. If I leave this alone, if I don't change the which parameter, the plot function will just give me a default 4. But there are 6 available if I just specify which ones I want. And I can pick and choose. I can have which equals 1, which equals 2, 3, whatever. Now, what R does, R will always label the largest 3 each time. And so if I look at these plots, you'll see that the largest 3, the ones that are sticking out the most, are there. So this helps us identify outliers. Now, and if I just leave this as is and get all 6, you'll notice that it just puts it on a grid so I can look at everything quickly. If I want to look at things individually, I just do one at a time. And we can see which ones we might want to consider as outliers for removal. When we look at the residuals versus fit, we don't want to see a pattern. Now, there can always be a little bit of bending. This is okay. I accept this. I'm not worried about this. But if I was to see like a clear trend in there, like a clear pattern, then I would want to adjust my model. Now, my QQ plot, we can see that we have the left-hand side is pretty hard below the line. Right-hand side is above the line. So this is absolutely not a normally distributed. And so if I want to do hypothesis testing, I'd have to be worried about this. So we do not have the right peakedness for our residuals to call them normally distributed. Most of the tests will be okay for hypothesis testing, but we would like to see closer to the line. Now, scale location, some people prefer this over the first plot that we looked at, where we take the fitted value and plot the square root of the standardized residual. Standardized residuals are, so we can rescale our residuals so that we always have a mean of 0 and standard deviation of 1. Now, linear regression, because of the additional theoretical aspect, that rescaling isn't quite right for what we should have because of the collinear aspect of what's going on. And so here, this is going to be adjusting to have it will be easier to identify if we truly have normally distributed off of this. And a lot of statisticians like the standardized residuals instead. And here's the Cook's distance. And so here, this is just a signal for us that there might be problems with these data points. And leverage is a way to think of leverage is that this is the amount of influence that a data point puts onto the entire model. And so when we fit a model, not all points have equal influence. Some have more, some have less. Well, if a point has a lot of influence, what that means is that it's taking the model and it's pulling the rest of the model away from the rest of the data points towards itself to avoid the error on itself, to avoid that squared error aspect. Well, if I have outliers, anomalies, well, frequently they end up pulling my model away from the rest to them. And so this is just a signal for me to double check to make sure that maybe I should have filtered these out. Maybe I should have capped extreme values on these individual observations. And here's another way to look at leverage with Cook's distance. Now, the variable importance will be coming, directly from hypothesis testing. What we're going to do, we're going to take the absolute value of our estimated coefficient, and we're going to divide by the standard error of the coefficient. And so this is actually, if I didn't have the absolute value bars, this would be a t-test like test statistic. So here, this is actually the absolute value of the t-test test statistic. And basically, if I see an extremely large value here, that means it's statistically important. And this gives me a idea of which variables are important. Why do I need the standard error in here? Well, if I have, let's say, one predictor variable it runs from 0 to 1, another predictor variable goes from 1,000 to 1,000,000. Well, the predictor variable for 1,000 to 1,000,000 is going to have a different variance than the 0 to 1 case. And so the coefficients are going to be trying to balance things out. And because of that balancing out, the raw coefficients are not sufficient for doing variable importance. If I was to go through and before I did my modeling, rescale all my data, all my predictor variables to have standard deviation of 1, then approximately the coefficients will correspond to variable importance. And so that's something I like to do to make it easier to identify what's important and what's not when I'm working through the process of rescaling my data first. Now, we can also check variable importance by the p-value. And so here's the coefficient estimate. Here is the standard error. Divided, we get that t-value. So the t indicates which ones are most important. And so that t-test leads us to a p-value, and some people like to use the p-value to evaluate it. The t or the p, whatever is easiest for you. The t is more directly connected to the coefficient, so that's easier to interpret. But p-values, a lot of people who have done like psychology, sociology, anthropology are more familiar with p-values, probably be more comfortable with that. Do whatever works for your project, for your stakeholders. Now, there are extensions of linear regression. These three that I'm going to talk about address the problem with that feature selection aspect. What it's going to do is it's going to look to see like, hey, I'm going to shrink coefficients to make sure that I don't have a problem with multicollinearity. And this also can push out predictive variables that shouldn't be in there, or just if it doesn't push them out, make the coefficients so small that practically speaking, they're not in the model. All right, so lasso works to make sure that the sum of the absolute value of coefficients is under a certain level. And lasso will actually kick out predictor variables that we don't want to keep. Ridge regression works to make sure that the sum of the squared coefficients are under a certain level. And so what this does for us, the reason why I like Ridge is that there have been times that because of like legal aspects, because of what was done in the past, because of my project, I had to be consistent with previous versions of the project, or particular stakeholders just wanted it a certain way. Like let's say that there are predictor variables I have to use because of either legally they were used, because in the previous version of the model, they use predictor variables and stakeholders want the same ones, or the stakeholder just wants to make sure that it's easier for them to understand. So they want to be more like regular linear regression, but I know that there's predictor variables I should not be using, or I know that there's multicollinearity. Ridge regression, what it'll do, it'll shrink those coefficients, but it will never actually send it down to zero. Lasso, how it does variable selection is it shrinks down the coefficient to zero, which means it's effectively not in the model. Ridge regression will shrink down the coefficient, not quite to zero, and so it'll be there. So if I need to legally talk to a lawyer, like, did you include this in your calculation? Yes, I did. So I can protect myself from that. That one's been that was really important where I worked before. And ElasticNet is a combination of lasso and ridge regression. Now, I'm going to talk about these three deeper in another video, but for now, I'm just showing you how to fit using the cross-validation function. And so this function will give us a collection of penalty parameters for the regulating of the coefficients. And then it's on me to go and extract what is the best for that, and then to make the prediction off of there. And so we can see here, I'm just showing you how to make the prediction afterwards. All right, so now you got some homework problems to work on. It should be pretty straightforward. This linear regression is absolutely the most important model to understand, the most important model to be familiar with. Generalized linear models and neural networks are built up off of linear regression. Much of statistics is built off of linear regression. A lot of concepts in statistics and experimental design are built up off of the concepts that have a foundation in linear regression. And so this is an absolutely critical thing to understand. Now, is it going to be your best predictor? Probably not, honestly, but it's a good benchmark, and it's fast. Since it's fast, it's usually worth it to just run it just so that I can get a feel for what's going on. All right, well, that's all I've got for you. Life is short. Do math.